When archaeologists unseal Egyptian tombs that have been buried for thousands of years, they occasionally find pots of honey left as offerings. Even after 3 millennia, the contents remain perfectly edible. In most cases, nutrient-dense foods are programmed to break down. They rot, they ferment, and they are quickly reclaimed by the microscopic fungi and bacteria that drive biological decay. Honey is an outlier, especially considering its source. It begins as flower nectar, a fragile solution of sugar and water that would normally spoil in a matter of days if left in the open. To understand how this liquid reaches a state of permanence, we have to look at the specific chemical and physical defenses bees use to stabilize a highly perishable raw material. The preservation process begins before the bee even returns. While foraging, the bee mixes raw nectar with specific glandular secretions stored in its honey stomach. The primary catalyst in this mixture is an enzyme called glucose oxidase. When glucose oxidase interacts with moisture in the nectar, it produces 2 distinct byproducts, hydrogen peroxide and gluconic acid. As gluconic acid accumulates, the nectar's pH level drops from a neutral state into a highly acidic range, between 3.2 and 4.5. This shift in chemistry renders the nectar toxic to most invading bacteria, replacing a welcoming food source with a potent antimicrobial barrier. The second defensive phase is physical. Worker bees position themselves over the honeycomb and vibrate their wings to circulate air, aggressively evaporating water. After 7 to 15 days of continuous fanning, the moisture content of the liquid drops to a precise range between 17 and 18%. This creates a supersaturated hypertonic sugar solution. In this state, honey uses osmosis to physically attack microbes. Because the sugar concentration is so high, it pulls moisture out of any bacterial cell that enters the solution, causing the cell to dehydrate and shrink until it can no longer function. This mechanism ensures that even if a pathogen survives the high acidity, it lacks the water required to reproduce and spoil the food. Because its water content is so low, mature honey is highly hygroscopic. If left exposed, it immediately begins absorbing moisture back from the surrounding air. To prevent this, bees seal the honeycomb cells with a cap of pure white wax, creating a physical barrier against ambient humidity. The combination of chemical acidity, osmotic dehydration, and a moisture-proof seal completes a system that effectively isolates the honey from the forces of decay. Once honey is removed from the hive, its longevity depends entirely on how well that isolation is maintained. If honey is harvested in high humidity or stored in an unsealed jar, it begins to draw water from its environment. This chart tracks the breaking point. Once the moisture content crosses the 20% threshold, the honey's density is no longer high enough to maintain osmotic pressure, and the liquid becomes susceptible to fermentation. Temperature is also a factor. Mass-market honey is often subjected to high-heat treatments to keep it liquid on shelves, but this process breaks down delicate enzymes like diastase. When the temperature spikes, the gauge shows the chemical damage. High heat destroys the natural enzymes and triggers the production of HMF, a compound that marks the degradation of the honey's quality. In a few minutes of overheating or exposure to moisture, the delicate chemical balance the bees spent weeks establishing is effectively neutralized. Honey has the capacity to last indefinitely, but only if the conditions of its creation are respected. To maintain its shelf life, the rules are simple. Keep it raw, avoid high heat, and ensure the container remains airtight. Every jar of pure honey is the result of a specific sequence of enzymatic chemistry and physical dehydration, a biological system of preservation that requires no further human intervention.